Okay, in this example, we're going to work with a clock. So hopefully you're familiar with standard clock notation. I'm going to draw sort of what the clock looks like on the board. I can't do the perfect circle, but it's good enough. So this is our clock. As you know, a clock has 12 hours. We can draw kind of the quarter hours. We have 12, we have 3, we have 6, we have 9. If we wanted to, sure, we'll draw hours 1 and 2. 4 and 5, 7, 8, and 10, 11. So we have this clock with 12 hours. And a clock, of course, has 2 hands as well, right? We have a little hand and a big hand. We're going to imagine just a little hand for this example. So we'll imagine a little hand, and we'll say it starts out pointed at 3. Okay. Now, in general, of course, the little hand is going to move at a steady, constant pace, going clockwise, right, as it ticks away the day. In this case, we're going to imagine the little hand moving randomly. Specifically, we're going to say that it moves clockwise, so regular 1 hour, each step with probability 1/2. It can also move counterclockwise with probability 1/2, 1 step. And we're going to say that these steps are independent. So let's say we start here and we randomly move to 4. Then from 4, we also have equal probabilities of going up to 5 or down to 3. And we kind of keep like wandering around the clock as that goes. So independent steps, equal probabilities of both directions. Okay, so that's our setup of our clock, and the question we want to ask is, what's the probability that we hit midnight before we hit noon? Okay, and to fully clarify what we're asking here, we have to clarify one other thing. We have to say that this is 3 o'clock p.m., okay? And the reason we say that is because midnight and noon occupy the same physical location on the clock, right? They're both at 12, but we're not thinking in terms of physical location, we're thinking in terms of temporal location. So we're going to say that midnight is if you hit 12 going clockwise, right? If you hit 12 from this side, whereas noon is if you kind of backtrack, right? We're starting at 3 p.m., noon is if you backtrack and hit 12 counterclockwise, from the counterclockwise direction. So it doesn't just, it's not just the location of 12, it's how you get there that it defines if it's midnight or noon, okay? Great, so we've got our setup, we see our clock, we have what we're trying to find, and this is the point where pattern recognition becomes really important, like trying to see what type of problem this is, what type of problem this is similar to, which will allow us to decide like what types of tools we can actually use to kind of solve this and solve this pretty quickly. So hopefully you're thinking, you see this kind of particle, it's moving around in the circle, it's sort of a random walk. Hopefully you're thinking of Gambler's Ruin, okay, so. And a quick refresher for what Gambler's Ruin is. The setup of the problem is we imagine 2 gamblers, gambler A and gambler B, generally we call them A and B, and we imagine them playing a game with N dollars, right? And we use this line to denote the amount of money that A has, so player A. So player A starts with I dollars, and he can either go up to N or he can go down to 0, okay? And the way we imagine the game being played is every single step, player A has probability P of winning $1, so taking $1 from player B and moving up to I+1, and probability Q equals 1 minus P. This Q equal 1 minus P is standard notation. A lot of times Q is just known as 1 minus P. Or probability Q of going down 1 step to I-1, and it kind of goes from there. Each of the steps are independent, so once we get to I-1, we have similar sampling, like P probability up, Q probability down. Okay. So now the key, we know Gambler's Ruin, we have our clock question, and the key is to connect them. How can we sort of connect these 2 problems, make this into this structure, into the Gambler's Ruin structure, which allows us to use the tools we know from Gambler's Ruin to actually solve it. So the way we want to make this look like this, well, this is a circle, right? And this is a line. So first thing we want to do is make it look like a line. The way we can do that is by breaking the clock, or like slicing it. We want to slice it at 12, right? Imagine cutting it at 12 and flattening it out. You could think of it if the clock was a string, right? We cut the string here, and then we pull the string and flatten it out on the line. So imagine cutting it, pulling it out on the line, and that means that we're going to start right where the little hand is. We can think of the little hand location as the money that player A has. So we're going to start at 3. That makes I-1 automatically 2. And that makes I+1 automatically 4. We can also fill in, we can think of 0 as noon, right? Because here we could go, 3, 2, 1, 0. We can think of this as 3, 2, 1's not drawn, but 3, 2, 1, 0. We can think of this as 12, and it's 12. It's also midnight. And finally, we can think of these probabilities Q and P, right? These are just the probabilities of moving up and down, which we know are given as 1/2 in this problem. So 1/2 probability of moving down each round, 1/2 probability of moving up. Okay, so now we've kind of sort of transcribed our clock into Gambler's Ruin, and we want the probability of, if we start here, hitting midnight before noon. Well, this is actually a probability, this is the major result of Gambler's Ruin, right? Like we've solved this. We know that the probability when P equals 1/2 is just I over N, or the starting location of the starting location of the little hand, the amount of money Gambler A has over the total number of hours or money in the game. And we know here we have I is 3, right? We start at 3, and we have N is 12. Okay, so 3 over 12, which is also 1/4. So we do a quick sanity check, as we should always do with our answers. This makes sense that it's less than 1/2, right? We're probably going to hit noon before we hit midnight because we have a much shorter way to go. We just have to go 3 hours instead of 9 hours. So that makes sense. Yeah, and we also got a valid probability, right? We got something between 0 and 1, which is important. So the key with this problem was, of course, recognizing that we had Gambler's Ruin, and you saw once we knew it was Gambler's Ruin, the solution was almost immediate. And this also shed some light on sort of our relationship with Gambler's Ruin. Like, we are not as interested in how we solve this. What we are interested in is recognizing when something is Gambler's Ruin and then being able to use the result. So knowing this result based on turning something into Gambler's Ruin. And of course, when P does not equal 1/2, we have a different result. It's a little more complicated algebraically, but it's sort of the same idea.